Hello everyone, it is September 13th, 2023, and this is the libhal meeting. Alright, so for the agenda today, we're going to go over handling driver lifetimes in libhal. This is something that I've been thinking about for a while, and I think I finally just pulled the trigger on it. I've been spending a lot of time trying to figure out how to make it work and work well. So let's get into it. So the agenda is going to revolve around this. So first item is going to be, what is an object lifetime and why does it matter? How do object lifetimes impact libhal code? Proposing libhal's new philosophy on object lifetimes, a mechanism for supporting libhal object lifetime goals, and how to support adapter functions. Or more to say, really, how do we use adapter functions going forward? So the first thing is, what is an object lifetime and why does it matter? Now today I'm actually going to go into detail about this one particular subject, just so that there's a record and a recording of me explaining how I feel about it and why we're going in this direction. And also making sure that the requisite information is presented as well. So object lifetimes refer to the lifespan of an object in programming from its creation to its deletion from memory. Every object in C and C++, and most languages in general, have some sort of lifetime constraint on their objects. Now, I kind of want to show what a stack looks like in a normal program. So for example, I want to kind of show that we have some function called start. It allocates some buffer of 8 bytes and then calls foo. And you can kind of represent this as part of the memory stack going down. And I actually just realized that the order of these slides might have been better off in a different order, but I'll go with this for now. Before we get any further, I just want to talk about how memory is laid out when you call functions in a program. So first, whenever you have memory for an application, you have some high value point in RAM that's going to be considered your stack. From the top of your stack is where your code will execute. Every time it wants to allocate memory for a function to run, it moves the stack pointer down. And it considers everything that's above it to be memory that it can control. Whenever you call a new function, one of the first things that it does is it takes the address of where it was before, puts it onto the stack, then moves the stack pointer even further down, and then everything above itself from the previous location ends up being where its data is, and so on and so forth. Same thing happens here. Start will move the stack origin down. This does not map out to what's here. Basically, it moves it down 8 bytes. Then it calls foo, which then places where the return link was, where this location is in this function, onto the stack. Then it calls itself. First thing it does is allocate all the stack memory that it needs. So it allocates an integer, moves the stack pointer down, and then it calls bar, and so on and so forth. This allocates float and int, then calls baz, does whatever it needs to do, and this is the active frame at the end, and then when it calls back out, it subtracts the stack pointer up, looks at the address at the location, and then returns. And this continues on until it gets all the way back down to the start. If it ever goes back down to the start, you may have a program that runs forever at a certain lower stack frame. So that's pretty much how stacks work. And that's how we usually allocate a lot of our memory. A little plus and a little extra note for people. You may think that, okay, if we have a lot of variables, that means it's going to take longer to allocate all of them. Well, no. Your compiler should be able to figure out how much data is inside of a stack frame for all stack frames. Therefore, all it needs to do is do a single subtraction to allocate all the memory that it needs. Here we can kind of see how this would go out for a theoretical program. So the arrow to the right represents each branch event, and the arrow going down represents the stack growth. So here we have a main function with whatever memory it's using up. Then it calls setup, that becomes a new active function. Then we call init, it uses up more memory. And then we call some power function. Let's say we're powering on some peripheral, some device. We're going to turn it on. Then we go back to init, we do some more work in init. Then we call enable. This is like after we've done all our work we need to do, we're now going to call a function that turns on the device and tells it, hey, you're now ready to start operating. Then we go back down to init, do whatever work we need to do there. Then we call back to setup. Then we go back to main, and the main goes, oh, I have everything ready that I need to do. Then it calls app, which takes up a lot of memory. That is how a stack grows and then shrinks depending on all the different functions there. This is important because it's going to lead into our next item here, which is what's wrong with this code? Now, if you've just started programming, this might be one of those things where it's like, pointers, I got to figure out how this thing works. But if you've been programming for a bit, you'll see immediately what the problem is. So integer a will only exist for the duration of this function. You create it inside this function, then it goes away. Once the function goes away, the memory pointing to a, or that was referred to a, will no longer be valid. Reference to a creates an address to where a currently is. And now once you return from this function, you get what's called a dangling reference or dangling pointer. We have a little example up here. We have main, then setup, and then something that calls foo. Foo in its data holds the value a. When we return an address, we're returning an address to this old location. When we send that back up to setup. Now let's say setup thinks, it has been allocated in some way that I can use. It will start using it. And then let's say it set the number to 110. Then bar comes in. It allocates on top of B. On top of what A was, because it's in the same spot now. And let's say it's a float. The way that the binary representation for a float and integers are very different from each other. So it does some work with the float, returns back up, and now setup has this value of A, this pointer to A, that now has a wildly different value. This is undefined behavior for the most part. We don't know how a particular bit of code will react with such a change that happens. In general, a lot of times when we're lucky, it simply just segfaults us. We hit some null pointer and it causes us to access some memory location that's so high, the device is like, I don't know what this means. I'm going to have your fault handler handle this. What's bad is if you have a variable that's being overwritten by another variable similar to it, and it just allows your code just enough to be able to work. Undefined behavior. So now, why is this code okay? So, and this is the picture I believe I should have had in the front, but here we have a global variable, b, and it'll last for the entire lifetime of a program. Then if we also use the keyword static, we get the same effect. We basically give this particular variable static memory duration. Global variables by default have static memory duration. This means that if you were to return the address of B, well, it would always be valid for the entire lifetime of the program. So returning back this address, not like it's going to be destroyed. It's going to be here forever. Static allows it to have the same property, except doesn't allow it to be accessible outside of this function. It's only accessible within the function. And you can return a reference to that so that something else on the outside could be able to manipulate this variable that's inside the function. So now B and C both live forever until the program ends. So why not use this for everything, you might think? Well, because it'd be a waste of space. Things like a quick counter or a float to do some calculations doesn't need to exist for the entirety of the program. It actually ends up using up space called data and BSS. The way that a typical application in C++ is designed is in this way. Now, it's a little different when you're working with microcontrollers because a lot of things can be, a ton of things can be different here. But for the most part, when you execute something that's a C++ program or a C program or probably even a Rust and other type of language program that actually gets compiled down, the first thing that gets loaded into RAM is the text section. This is where all your code is. After that, you then get data, which is all of your initialized variables. So if I set this b equal to 5, the compiler needs to store the 5 somewhere and then map that 5 to that b so that when I run through the start of the program, b gets initialized to 5 before main gets called. Next up, we have the BSS section, which in general, we just have the BSS section, which is a whole space of RAM that is unallocated. And that area, I believe I forget what standard requires. I don't know if C specifically requires this, but I know newlib does, which is like the implementation for printf and malloc and puts and all the math functions. That requires that the BSS section be zeroed out. It relies on that section being zeroed out for it to operate properly. But that might also be a C thing. I'm not too sure. After that, we have the start of heap. Oh, do I have a question? Okay, sorry, I thought I heard something. So yeah, then that becomes the start of heap. And on the opposite side, we have the stack. The stack is where all your functions allocate their memory, and the heap are areas where your application can allocate memory if it needs dynamically allocated memory. We'll go into more about this a little bit later. What you end up doing is you end up transferring variables that would have normally been on the stack into the BSS or data section. And these spots live until the program dies. Whereas the stack is always fluctuating and changing. And the heap, well, we'll get to that in a little bit. So what about dynamic memory allocation? Well, heap allocated objects lifetimes are controlled directly by our program. For example, if we want to create a new integer based out of the heap, we can just simply do new int, store that inside of a pointer, do some work with it, and then when we're done with it, we're like, okay, I don't need this thing anymore, we can delete it. Very powerful tool, and very useful for a lot of different situations. Although I will say, directly controlling object lifetimes like this with new and delete is a bad idea. I will say a lot of new languages and people who are proponents of them will like to give this really bad, in my opinion, look to C++. They'll say, "Oh, C++ is so bad. Look, you do new and then you dangle, forget to remove it by deleting it, and then you dangle it, or you end up deleting it twice on accident, or for some reason, and then you get a double free, which ends up causing the thing to segfault. You could run into problems." Now, you could see some people using new and delete manually, but you almost never should ever do that. You should almost always be using smart pointers, such as unique pointer, shared pointer, unique or shared pointers. You can look up those on your own, but basically the lifetime starts when you create it, and then only when you have no way to access this particular label or a copy of this, not really a copy, but a moved version of it, then does the actual object die. So it only can escape you if you end up not actually using it, or when you stop using it. Heap allocated objects wrapped with smart pointers are great because they allow space to be freed up when they're no longer useful. So why not use dynamic memory allocation? Well, in general, dynamic memory allocation is avoided in embedded systems for numerous reasons. I'm not going to go into it here. You can ask ChatGPT or Google. It's such a Googleable and easy to find answer that I'm even certain that ChatGPT will give you a fantastic answer. One thing to note is that Mr. C states that dynamic memory allocation is okay so long as you allocate memory early in the program at setup. Two, does not dynamically allocate during the runtime of the program, and 3, does not free the memory. Now, this is based off my memory. I don't know if this is exactly what they stated. I should have looked it up. But for the most part, they do mention the fact that you need to allocate all your memory as early as possible, and that you should not deallocate, I believe. And actually, strictly, you should not be allocating memory at runtime. The quick reason for that is that if you keep allocating and deallocating memory in different sizes, eventually you get memory fragmentation. And there's another issue, which is that how does your program handle the situation in which allocations fail? And can it gracefully handle that? And it's very difficult to gracefully handle that scenario. In most programs, you should just simply let the process die. But you can't always do that when you're a pacemaker. When you are a control system for a plane, those aren't really acceptable. So there's a couple items to go into. But yeah, these rules effectively have the same result as dynamically allocating. This should be statically allocated memory. With the difference between running out of RAM is easier to know at compile time with statically allocated memory than with dynamic. So with dynamic memory, where you have to ask the system at runtime, hey, do I have enough memory? You have to run it to get there. Whereas with statically allocated memory, it will tell you at compile time if you ran out of memory. You would also be able to see the percentage of data that's used up, as well as how much you'd have for stack. So you'd be able to look at this at compile time without even having to run the program and see if you're in a bad spot. Also, one other thing is that smart pointers, I did look into them. I was actually considering relaxing the dynamic memory constraint on libhal if smart pointers were worth it. I'm not convinced that they are. I believe that they have 5 vtable entries, which is a lot, all which have to do with destructing and deleting the object. I bet they all are really important. They all need to be there. But because of them, it results in a lot of code bloat, not just in having the vtable entries, but also the code that follows with them, and the fact that the entries change for every single variation of type. And there's like multiple ways you can mix and match and set up the template parameters for a smart pointer or shared pointer, to the point where I feel like it might end up being more memory than simply going with statically allocated objects. So yeah, so that's why we don't really use dynamic memory allocation. Now, how do object lifetimes impact libhal code specifically? We've been talking about a lot of jelly bean examples, but let's look into something closer to a real example. Here's something that I took directly from the RMD demo for LPC 7048. I trimmed it down to get rid of a lot of the extra stuff that was there. So here we have a clock object. We're going to get its frequency, and then we're going to take this seat frequency value, and we're going to throw it in here. No, this is actually a singleton. Yeah, and I'm probably actually going to change the APIs for clock. They're going to be backwards compatible, but I'm going to follow what I did for STM, which is just have free functions for everything. But yeah, no. So here we have static DWT counter. And then we have, some static buffer, and then we have UR here. We created a new UR at 0, and then we return this back up. This probably looks fine for the most part, if you don't really catch it. But there is one mistake here. This is missing static here. Because of this UART 0 is being passed up out of the stack, and hopefully your compiler will tell you, hey, warning, you are returning a address of a local variable out of your function. And just a little side note, I've seen a lot of people compile their code with a bunch of warnings. If you're wondering why your code doesn't work, you should definitely look at those warnings and just clear those up, just to ensure they're not the actual issue. Just want to put that little PSA out there. But yeah, but sometimes health check and other things will confuse the compiler to the point where it's like, okay, there's too much stuff happening. Can't really deduce whether or not this thing is actually a local variable or not. Therefore, it may skip that particular warning. This is problematic because you'll know at runtime if something goes wrong. And this happens enough and frequently enough to the point where I thought, okay, is there any way that we could effectively fix the lifetime issue? And this also made me think about lifetimes in general when it comes to these objects. Like, what other implications does having what other things about the object are causing potentials for issues? So here's where I propose a new philosophy for libhal on object lifetimes. Number 1, drivers should have static memory duration. This is to prevent the issues we talked about before. Drivers shall not be copyable. So what does it mean to copy a driver? So here's the thing. You can copy things like strings or vectors in C++ or other objects in C++. But does it really make sense to be able to copy a driver? Now let's say you want to talk over I2C. And you copy the driver between two systems. So for one particular I2C, you start using it, you start a transaction. And let's say you use them across different threads. I have two drivers, they're separated, there's no threading issue, I'll just use them separately in different threads. So one of them tries talking to it and modifies the state of the peripheral underlying. And then the other one comes in and says, I want to restart the communication, and also starts reconfiguring the underlying registers as well. Now these two objects have completely different states about what they believe the hardware is currently in. So one of those transactions that you're doing with a sensor or something like that will get screwed up. It's even worse if they try talking to different things. So at that point, we can just consider whatever happens here to be undefined behavior. But there's a lot of bad things that can pretty much go on when you have a copy of a certain of a driver. They're both pointing to the same resource. And that's kind of the idea, is that drivers typically manage a single resource or a subset of a resource. And having copies of that to point to the same resource is not a good thing to have. So that's why copies are probably are going to be banned in our drivers. The next one is that they shall not be movable. Now, the one question comes up is, why would you want to move a driver? You can move it around up and down a stack, and it'll just live on the stack if you wanted to. That's fine. But we don't gain anything from this. And so long as it continues to be movable and you can move it around the stack, it's pretty much allocated as long as you end up needing and using it. But really moving it doesn't really give that much value. But also, I think the worst part about this is that the consequences of allowing movability is that it requires a developer to write a move constructor. And in general, if it's not the default move constructor, then it's not trivial. And this has been a vector for bugs that I've actually introduced multiple times. I added in movability to quite a few of the drivers from the statically allocated drivers that we had before. And in doing so, it resulted in the exception handlers basically pointing to nothing and then causing a seg fault. You'd try to send a character to the UART and it would immediately just seg fault at that point. The reason why is because that, where the object was before when it set up interrupts, it told the interrupt controller, hey, here's where I'm located currently. So you can find my methods, you can find my classes, you can find everything. When it got returned up the stack, the old stack got eliminated and destroyed. And now that location where that pointer probably existed is now pointing to some random value that causes the thing to fault. So movability is not really useful, copyability is not really useful, and static memory duration is not really useful. The benefit of having these guys eliminated and then also statically allocating means that you know it's going to be allocated in one spot, stay at that one spot, and you're done. Now, the mechanism for supporting libhal's object lifetime goals is the static initializer. It's a template class that has that you must do the following in order for it to work. One, you have to inherit it. So you have to opt in. Every driver has to opt into using static initializer, but there's not really much we can do about that. There's no other way to build an object in C++. So it must inherit the static initializer T, where T is the type of the class. Must add a friend declaration for static initializer T, where T is the type of the class. Must private their constructors. This is just to prevent construction outside of using the static initializer. Technically, you can put them public if you wanted to have both options. I am still considering the idea of relaxing this particular rule for people or drivers or developers that feel that they have a need for a global constructor that bypasses the static initializer. Must take a pointer to a HAL status as its first parameter of all constructors, and must delete, move, and copy constructors. Now, it's actually this last bit here, you don't have to do it. Static initializer will do this for you. And this is what it'll look like. So here we do public inherit static initializer test driver, which is the same name here. This is a technique called curiously recurring template parameter, or CRTP, and it allows you to extend a driver as if you were its parent. So you can effectively extend different drivers to do whatever. This also allows me to delete all of the copy and move constructors from the static initializer, preventing this class from doing the same. And then here we have the constructor, which takes a status. Rather than creating a create or get function that returns a status, we're now going to use this thing called HAL redirect check. This basically takes the results of any call that is fallible, that could return back a failure state, and it saves it into the state of P status and then returns early if that ends up occurring. If there are no errors, it will return, if let's say this thing returns an int, it'll return that value out the back here, so you can save it. And then lastly, we have friend class HAL static initializer test driver. Here's a more grown-up example. This is something that I'm working on for libhal LPC 40. Just note that the old code should still work. I'm just adding in more constructors and adding in the static initializer class, but all the other APIs should still basically work. So old code is not a breaking change. But I may end up marking those particular API calls as deprecated in the next month. But we have our area where we set up our clocks. Seems like normal stuff, nothing too crazy here. We have our setup UART. Now there's a bit of interesting things that I'm going to be adding, which is these objects that really have zero size, effectively zero size. They have kind of like a byte, but they have effectively zero size. But what they really are is a type. So you just pass this object like type to UART or can, and that invokes a template constructor, and that template constructor could see if the port number that you chose is valid, something like that. We also don't even have to do an actual, what's the word I'm looking for? We may not even have to use a type. We could probably use some other things, but that's pretty much the idea. And then also in that same vein, we could have a constructor for that particular port number that allocates a certain amount of memory for that UART. One thing to keep in mind, though, is that if you change the buffer number between each subsequent call, you'd end up actually doing a compile time memory leak because you would redirect the pointer to what the UART looks at, and the other objects will pretty much get forgotten. That detail, don't worry about it too much. But the big part that we're looking for is the initialization. So here we have HAL LPC40 UART initialize 1. Note that we're not using a get function, we're using the initialize function. Create and get will be replaced with initialize just in general everywhere. That way we only have two ways of constructing things. You have initialize things that get initialized, which are actual drivers. And then you have adapters from drivers, which use the make protocol or make scheme. And you just return it back to a variable, and then you can use it like a pointer. So that's the idea, is that this now comes back acting like a pointer. It's not a pointer, it's a thing called an entity, but that's for in the next meeting. And then same thing goes for can. And then you return them up like you would like normal pointers, and you're good to go. Now note something about how initialize is designed. You can see initialize 0, 1, and 2 here. These numbers represent their what we call a storage ID, and I think we even have. Whoa! I'm missing a slide. Oh goodness. Okay, I don't know where that slide's gone. I thought I had all this stuff all good together, but basically, there's a thing called a storage key. Basically, it's just a template parameter that tells the compiler, "Hey, this is a unique function. You should statically allocate the values separately." So what you'll need to do is ensure that the storage key for every single one of your initialize functions are a unique value. One way to do that is to simply replace all of them with the line number. If you have all your drivers initialized in one place, you could just use the underscore line. You'll just take whatever line number is on the left-hand side and throw it right here, and that's a unique number. So long as you don't try to stack these on the same exact line. But if you end up having this across multiple files, you need to coordinate a little bit. But there are ways to get around this. The consequence of using the same number in the same for the same type is that you'll end up having the two variables colliding on each other, or basically there'll be a collision. They'll basically be looking at the same memory location that they had before. And whatever is the last initialize call will be the last initialize that gets implemented on that memory. I am looking at ways to try to eliminate, basically to cause an ODR violation if you ever use the same number twice. I basically want some way for the compiler to tell you that you made a mistake there. But I'm still looking into it. I'm also looking into a way that could potentially automatically come up with a unique number each time, or a unique instance each time, but I am finding that is seeming to be impossible. It may be impossible until potentially some new features in C++ 23 or 26, but even then it would still not be that ergonomic. So work is still being done to try to see if this can be improved. And then for adapter support, basically it works exactly the same. You'll initialize whatever thing you want. Excuse me. And then you'll pass this into whatever your make thing is. So in this case, we have an ADC mux. We want to separate out all the individual channels. So we will pass ADC mux in there, and then we'll say the channel that we want is 0. What this will do is actually statically allocate a an adapter from ADC, and it will bind this particular object's type, which is a unique type if you get the value here unique. This auto type here will actually be a unique value as well. And it'll bind the channel, the ADC type, the ADC adapter type, and then whatever this type is onto it. That basically allows it to act freely and statically allocate itself in its own specific way, ensuring uniqueness and separation between all of the different channels. It took a bit of time to figure out, but eventually I figured it out. But for the most part, as a user, you'll just use it like you did before. Just simply make ADC, whatever parameters you need to make that thing work, and then go. You're good to go. They too will allocate memory statically, but they do get a little more complex. So more internal details next time, but I will say that the main idea is going to be that you'll have whatever object you want to create, an initialize function. You have to remember to put in a unique number for each one of these. And so long as these numbers are unique, these values out here will work appropriately. And that I am working on ways to come up with unique ways of generating these objects. And that's pretty much it.